Okay, so your next example with two-dimensional forces is going to look at now an accelerating object rather than Fnet being 0. So example 2.2.3 says you are pulling your little cousin in her wagon at an angle of 40 degrees above the horizontal. The combined mass of your cousin and the wagon is 24 kilograms, and there's a force of friction of 6 newtons backward acting on the wagon. What applied force is required to cause the wagon to have an acceleration of 1.5 meters per second squared forward? Okay, so I'm just going to draw the situation. And normally when I picture a wagon, I picture a little red wagon. Okay, so we're going to draw our wagon in here. We're going to draw our little cousin in the wagon. Okay, and their combined mass is 24 kilograms. Okay, and then there's you. Okay, and you are pulling the wagon so that the wagon creates an angle of 40 degrees with the horizontal. Okay, so we should always start with, especially now that we're getting into more forces and actually having an Fnet, drawing a free body diagram. Okay, so we have our combined mass, which is 24 kilograms. Okay, on that object, we know because we are on a flat horizontal surface that we are going to have the force of gravity. Anything on Earth is going to have the force of gravity, and because we're on a flat horizontal surface, we know we're going to have the force of normal that's acting straight up. Okay, and those two are going to be equal but opposite to each other. Okay, next thing we know is I'm going to draw my horizontal in here, is we know we have our applied force up in this direction that is being applied at an angle of 40 degrees. Okay, and then lastly we know what the force of friction is. Okay, and we know we have some force of friction. I'm going to say it's kinetic because we're moving, and that force of friction is 6 newtons. Okay, so obviously for us in this problem, we're just going to say anything forward is positive. Okay. Now, in this situation, because they've given us the frictional force, I really don't have to look at the applied force that much in the y direction. Okay. Now, if we were looking at solving for the frictional force, remember what that means is we need to know what the force of normal is. And in the case when we actually have an applied force in this direction, the one thing that we cannot say is that these two forces are equal. Okay, because I do have some force that's being applied up in that direction. So technically, your force of normal is actually going to be a little bit less than the force of gravity acting on the object because you're helping pull up a little bit. Okay, but because we're not concerned with the y direction here, because they've already given us what that frictional force is, I'm not even going to consider the y direction. So let's just look at the applied force in the x direction. Okay, if you'll notice, the only forces that actually contribute to the acceleration of the object are the applied force in the x direction and that force of friction that acts back. Okay, those are the only two things that are going to cause it to act or accelerate in that direction. Okay, so we need to go and solve for what Fnet is. Okay, Fnet is equal to, well, in this case, the applied force in the x direction acts forward, so I'm going to put it in as positive. Okay, and we're subtracting that force of kinetic friction because it acts in the opposite direction. Okay, remember what we're actually trying to solve for is that applied force. Okay, so what I'm going to do is substitute, we're going to substitute Fnet for mass times acceleration, because we know any Fnet is equal to a mass times an acceleration. Our applied force in the x direction is going to be equal to the magnitude of that applied force multiplied by x is adjacent to my 40 degrees, so I'm multiplying that by cos theta, and that's still minus the force of kinetic friction. Okay, so really when we look at solving for FA, we're going to move the force of kinetic friction over. So you get Fnet plus that force of kinetic friction equals the applied force times cos theta. Okay, so we're going to divide out cos theta. So that means the magnitude of our applied force is going to be equal to the combined mass times the acceleration plus that force of friction divided by the cos of the angle that we are pulling at. Okay, now that we've rearranged, we can simply plug in our values and solve. Okay, so the mass is 24 kilograms. Multiplied by our acceleration, which is 1.5 meters per second squared forward. Right, so it's a positive 1.5. Oops, sorry. And then that's plus our force of kinetic friction, which is 6 newtons. Which, if you think about it, when you do the rearrange, makes sense. We're talking about our applied force here. So for you to actually get this Fnet, you're going to have to overcome the force of friction, right? And then whatever is left over creates that Fnet that allows us to accelerate at 1.5 meters per second squared. Okay, and this all gets divided by the cos of our angle, which is 40 degrees. Okay, so 24.1.5 is 36 newtons plus 6 newtons, all divided by cos 40. So what we're getting is 42 newtons divided by cos 40, which is, excuse me a second, so cos 40 is 0.76604. So when we divide 42 by that value, we end up with 54.83 newtons. Okay. Now remember, this actually solves for that entire magnitude. So this is the applied force that we are looking for. Okay, so the applied force that we have to apply in order to cause an acceleration of 1.5 meters per second forward is 55 newtons if we use our significant figures. Okay, and then don't forget to add the direction of 40 degrees above the horizontal. Sorry, my dog's ripping around right now. Okay, and that's the final answer to our question. Okay, this is Wanny signing off, and may the force be with you.